SwayamPrabha. Digital India. Educated India.
Good morning everyone. Today we will discuss something more about thermally fully developed flow in a pipe. Now we have already analyzed hydrodynamically fully developed and thermally fully developed flow in a pipe with uniform wall heat flux boundary condition. We will now analyze hydrodynamically fully developed and thermally fully developed flow in a pipe with uniform wall temperature boundary condition. So our governing equation is rho Cp U del T del X equal to K by R del R of R del T del R. Since it is hydrodynamically fully developed flow, V component of velocity is absent. Now we can define theta as T minus Tw divided by Tc minus Tw, where Tc is the center line temperature and Tw is the wall temperature. We also introduce eta equal to R by R naught and Z equal to X by R naught, and we introduce uppercase U, which is function of eta, is U by Um. Uppercase U is function of R by R naught, and we can write this as U by Um, where Um is the mean velocity. So here we can write rho Cp Um into U eta divided by R naught del T del Z. Del X of T becomes del T del Z equal to K R naught square 1 by eta into del eta of eta del T del eta. Here we do some regrouping. We bring in nu and then divide by nu. The purpose is from this group we are trying to get nu by alpha. K by rho Cp will give alpha, nu by alpha will give Prandtl number. And in this group we multiply with 2 and divide with 2. So Um twice R naught, which is diameter, R naught is the radius of the pipe, divided by nu, that will give us Reynolds number. So we get Prandtl number into Reynolds number based on tube diameter. R naught is the tube radius and D is the diameter, by 2 U del T del Z equal to 1 by eta del eta of eta del T del eta. So we have already defined that T minus Tw divided by Tc minus Tw is theta. So T can be written as Tw plus Tc minus Tw into theta. And Tc we know is function of X, thereby it's function of Z also. So del T del Z is theta del Tc del Z, we can get from here. del T del R, we can straight away get Tc minus Tw del theta del R, and del T del eta is Tc minus Tw del theta del eta. So in this equation, we do the substitution of del T del eta and then del T del Z, and we get this is Prandtl number into Reynolds number, Peclet number, u theta by 2 dTc dz equal to 1 by eta del eta eta d theta d eta into Tc minus Tw. This can be rearranged as Peclet number dTc dz divided by Tc minus Tw equal to 1 by eta del eta eta del theta del eta divided by u by 2 theta. U is function of eta, theta is also function of eta. Now this group is function of eta and this group is function of z. So we have already separated the variables and we can bring in the separation constant minus lambda square. So from here we can write Peclet number into dTc dz divided by Tc minus Tw equal to lambda square, which will give us basically variation of central line temperature Tc as function of z equal to Tw plus C e to the power minus lambda square z by Peclet number. So this is, as I said, variation of central line temperature with z given by Tw plus C arbitrary constant e to the power minus lambda square z by Peclet number. The second part will give us 1 by eta del eta eta del theta del eta plus lambda square by 2 into u theta equal to 0. And already we know u by um in a fully developed tube flow or pipe flow, u by um is given by a parabolic variation which is given by twice 1 minus r by r naught square or twice 1 minus eta square. So we can substitute u and then this equation gets into this form theta double prime plus theta prime by eta plus lambda square into 1 minus eta square theta equal to 0. We can see that this is second order equation and we have to find out suitable technique for solving this equation. The equation is to be solved using the following boundary conditions at r equal to 0, t equal to tc, which means at eta equal to 0, theta equal to 1, because theta is given by T minus Tw divided by Tc minus Tw. So at r equal to 0, t is Tc. So at eta equal to 0, theta equal to 1. At r equal to r naught, t equal to Tw. So at eta equal to 1, theta equal to 0. The solution of the above equation is an infinite series and we write that series as theta equal to, series is Cn eta to the power n, n equal to 0 to infinity. n varies from 0 to infinity. So we can write theta as C naught plus C1 eta plus C2 eta square plus C3 eta cube up to Cn eta n. Then first derivative theta prime we can write as C1 plus twice C2 eta plus thrice C3 eta square. This way we can write n plus 1 Cn plus 1 into eta to the power n. And theta double prime also we can write as twice C2 plus 6 C3 eta. This way we can go up to n plus 1 n Cn plus 1 n power eta power n minus 1 plus n plus 2 into n plus 1 into C n plus 2 into eta power n. So these are the derivatives. After finding out theta prime and theta double prime, we have to plug in here in this equation. This is the governing equation. So theta double prime, we write theta double prime plus theta prime by eta, we write theta prime by eta plus lambda square into theta. So plus lambda square into theta equal to, we take lambda square into eta square into theta on the right hand side. Lambda square into eta square into theta on the right hand side. Now in this equation we can equate the equal powers of eta for the validity of the equation, and this way we can collect the coefficient of the equal powers and try to obtain their value. We will see C1 equal to 0, then 2C2 plus 2C2 plus lambda square C0 equal to 0, 3 into 2 C3 plus 3C3 plus lambda square C1 equal to 0. This is we are collecting from here, from this equation, equal powers of eta. So 4 into 3 C4 plus 4 C4 plus lambda square C2 equal to eta square, lambda square C2 equal to lambda square C0. 5 into 4 C5 plus 5 C5 plus lambda square C3 equal to lambda square C1. So this way we can go up to n plus 2 into n plus 1 C n plus 2 plus n plus 2 into C n plus 2 plus lambda square Cn equal to lambda square Cn minus 2. Just, little meticulous collection from this equation, equal powers of eta. Now we can see C1 equal to 0, and since C1 equal to 0, from the third equation we get C3 equal to 0, and since C3 and C1 equal to 0, from the fifth equation we get C5 equal to 0. This way we will get all odd coefficients as 0. So finally we get this in this equation. If we substitute n equal to twice m, we will get twice m plus 2 into twice m plus 1, c twice m plus 2 plus twice m plus 2 into c twice m plus 2 plus lambda square c twice m equal to lambda square c twice m minus 2. Now here, if we collect coefficients of c twice m plus 2, we'll be able to, if we take c twice m plus 2 common from these two terms, within bracket we'll get twice m plus 2 into twice m plus 1 plus twice m plus 2 into 1. So basically again we'll get twice m plus 2 square. into twice m plus 2 square into c 2m plus 2 plus lambda square c 2m equal to lambda square c 2m minus 2. So exactly from here, as I said, that 2m plus 2 square into c twice m plus 2 we are getting if we rearrange these terms. So twice m plus 2 square into c twice m plus 2 plus lambda square. Here we get lambda square c2m. Lambda square c2m equal to right hand side lambda square c2m minus 2. So from here we get c twice m plus 2 equal to lambda square divided by twice m plus 2 square into c twice m minus 2 minus c twice m. So we can generalize this term as c twice m equal to lambda square by twice m square into c twice m minus 4 minus c twice m minus 2. Generalization of this equation. Basically, we can get this equation which is valid for even coefficients. So therefore, we can write, so we have seen odd coefficients can be dropped, and now we can write theta equal to c, again we write very general expression, c twice n into eta to the power twice n equal to 0 to infinity, where c twice n is, from this expression we can write lambda square by twice n square into c twice n minus 4 minus c twice n minus 2, and this is valid for n greater than equal to 2. So we can also write theta equal to n summation of a series n equal to 0 to infinity c twice n eta to the power twice n, whereas series is given by c naught plus c2 n square plus c4 n4 plus c6 n6 and so on. Now invoking the boundary condition, we have not applied to this series boundary conditions as yet. Boundary conditions are eta equal to 0, that is r equal to 0, t equal to tc, that means theta equal to 1. Now if we apply that at eta equal to 0, theta equal to 1, we get c naught equal to 1. Then at r equal to r naught, that means eta equal to 1 and eta equal to 1, t equal to tw. So expression for theta is tw, t minus tw divided by tc minus tw. So in the numerator for eta equal to 1, we get tw minus tw, that means 0. So theta becomes 0. So then in this expression, again we substitute n equal to 1 and in this expression, we substitute eta equal to 1, eta equal to 1, theta equal to 0. Eta equal to 1, theta equal to 0. So c0 plus c2 plus c4 plus c6 equal to 0. And first one we obtained that as eta equal to 0, theta equal to 1. That gives us c naught equal to 1. And then at eta equal to 1, theta equal to 0, that gives us c0 plus c2 plus c4 plus c6, the even coefficients equal to 0. Then we keep writing from our expression for c2n. We can see this can be a general expression for the coefficients. So we write C2, C4, C6 from this general expression, and we get C naught in minus lambda square 4 C naught plus lambda square 16 into 1 plus lambda square by 4 C naught, lambda square by 36, 5 lambda square by 16 plus lambda 4 by 64 into C naught, and so forth, equal to 0. Now we can write then C naught into 1 minus lambda square by 4 plus lambda square by 16 plus lambda 4 by 64 minus 5 lambda 4 divided by 36 into 16 minus lambda 6 divided by 36 into 64, and so on, equal to 0. Utilizing the fourth power of the series, we can get this term, and then C naught is definitely not equal to 0. We have gotten C naught equal to 1. So these bracketed terms, we can equate them to 0, and by Newton-Raphson method, if we solve, we will get lambda as 2.704364. So we have now solved this equation with the boundary conditions, and final solution is given by this series theta equal to summation over n equal to 0 to infinity C2n eta to the power twice n, where C2n is given by this expression and n is greater than equal to 2. So with this we have to write the value of C naught equal to 1, we have found out, and lambda we have also found out, 2.704364. So this is the complete solution. Now we utilize this complete solution to find out the Nusselt number. In order to find out the Nusselt number in the pipe, we make use of governing equation. And then this governing equation, we transfer R to left hand side from right hand side and integrate between 0 to R naught. And after transferring R from right hand side to left hand side, we also integrate this with respect to R and set the upper limit and the lower limit, and we get K R naught del T del R at R equal to 0. Here we can write then rho Cp u theta by R naught dTc dz R dr, sorry, this will be theta by R naught, when we substitute del t del x in terms of del tc theta into del tc del z, theta R naught del dTc dz R dr equal to K R naught del T del R at R equal to R naught. And here to be mentioned that del T del R at R equal to 0 is 0. So when we set the limits at R equal to R naught, upper limit and lower limit, the term doesn't appear. So we get R equal to R naught. Now here we try to again rearrange these terms. What we do, we bring in K, and then we also bring in nu, and since K comes at the numerator, at the denominator 1k comes, that k by rho Cp becomes alpha, and we multiply with nu, divide by nu, to get basically we bring in um and divide by to get u by we again multiply by twice r naught and divide by twice r naught. So these are some arrangements to get little convenient form. I will explain. So here we get dTc dz divided by basically Tc minus Tw. This is nothing but theta we are writing as T minus Tw into Tc minus Tw. This theta is written in this way. And right hand side R naught, this is wall heat flux. K del T del R at R equal to 0. So we did this just to get nu by alpha here, which gives Prandtl number. This term gives Reynolds number. This gives dTc dz and divided by Tc minus Tw. Now we can write K into the remaining terms like R by twice R naught square, U by multiplied by T minus Tw. We multiply twice pi, divide by twice pi, dr, integrate between 0 to R naught, Q wall heat flux, Qw double prime. Here, basically, we try to do this in order to get, if we recall, when we applied the separation of variable principles, we separated out this term from the governing equation and set the separation constant. And this is a fully function of z. So that we do here again. So this is basically lambda square, and so this is lambda square k. So this is minus lambda square k by 2. We again multiply, we bring in 2 here, so multiply a numerator with 2 and again rearrange these remaining terms. Do it little carefully. Twice pi ur T minus Tw dr divided by twice pi r naught square equal to R naught into wall heat flux Qw double prime. So here we this lambda square by 2, we this we can even lambda square k by 2, we can will not participate in integration. So minus lambda square k by 4 we take out and then perform the integration. And this integration you can see one group is integration 0 to R naught u into t twice pi r dr divided by pi r naught square, and another group minus tw into 0 to R naught u twice pi r dr divided by pi r naught square. So here we can clearly see that minus lambda square k by 4, this is nothing but the bulk mean temperature. So this is Tm, and this is also basically this term is exactly equal to the denominator. So from here we get Tw equal to R naught Qw double prime. And then we can rearrange Qw double prime divided by Tw minus Tm into twice R naught by K. Now this QW double prime wall heat flux divided by TW minus bulk mean temperature, this is nothing but film heat transfer coefficient, into twice R naught, that means the tube diameter, pipe diameter by K, equal to lambda square by 2. So this is nothing but Nusselt number based on tube diameter. So we can write this as Nusselt number based on tube diameter equal to lambda square by 2. And lambda value we have already found out. We can 2.704364 and lambda square by 2 will give 3.656. So this is the expression for hydrodynamically fully developed and thermally fully developed pipe flow. Nusselt number for hydrodynamically developed and thermally fully developed pipe flow with uniform wall temperature boundary condition. And if we recall what we obtained in our last lecture is for hydrodynamically fully developed and thermally fully developed pipe flow for uniform wall heat flux condition, Nusselt number is 4.36. And today we have obtained for uniform wall temperature condition, it is 3.656. So for uniform wall heat flux condition, Nusselt number based on the diameter is 4.36. For uniform wall temperature condition, Nusselt number based on diameter is 3.656. Now we can, without going into rigorous proof, we know the results and we are just mentioning the results for similar situations, hydrodynamically fully developed and thermally fully developed flow in parallel plate channels. There Nusselt number is 7.5407 for uniform wall temperature and 8.2352 for uniform wall heat flux. Now if we consider that for tube flow or pipe flow, for uniform wall heat flux it is 4.36 and uniform wall temperature it is 3.65. Whereas for parallel plate channel, for uniform wall temperature it is 7.54 and uniform wall heat flux it is 8.2352. This seemingly here the Nusselt number is more, but one has to also understand, one has to recall or understand that these two expressions, the Reynolds number has been calculated based on characteristics length twice B, where B is the channel height. So this is based on twice B. Now this uniform wall heat flux condition and uniform wall temperature condition can be applied to hydrodynamically fully developed and thermally developed flow. Hydrodynamically developing and thermally developing flow. So basically we can get multiple combinations like flow is hydrodynamically developed or developing. Thermal field is fully developed or developing. And we also can get thermal conditions, uniform wall heat flux or uniform wall temperature. Now, a very useful, marvelous compilation of these results were done by R.K. Shah and A. London, Professor Shah and Professor London, and these are available for not only for tubes, for different other channels or ducts with square or triangular or different other cross sections. Now here we will just refer to the flow through circular duct or flow through pipe or tube, and we will from Shah and London's book we will reproduce the results for, you can see, Prandtl number 0.7, that means for the its flow of air, and you can see Nusselt number, this is for simultaneously developing flow, and this is for thermally developing flow. Simultaneously developing flow means the hydrodynamic boundary layer is also developing and thermal boundary layer is also developing. But this dotted case is hydrodynamically flow is fully developed, but thermally it is developing. And in this part, these two situations merge. That means flow is hydrodynamically developed and thermally developed. And these two are, this form line and this dotted line, these are for uniform or constant wall heat flux. Similarly, for constant surface temperature or constant wall temperature, we can get this one is simultaneously developing. That means hydrodynamically and thermally flow is developing. This is hydrodynamically fully developed and thermally developing. And this is hydrodynamically and thermally fully developed. Finally, for hydrodynamically and thermally fully developed constant heat flux boundary condition, we get 4.36. Hydrodynamically and thermally fully developed for constant wall temperature, we get 3.656, which has been written as 3.66. And this axis, you can see x by d divided by Reynolds into Prandtl. So, NUD is plotted against the dimensionless parameter x by d REPR. This is Nusselt number, this is x by d REPR. Or this can be also called as Graetz number. Graetz is a very well-known scientist who gave solutions for hydrodynamically developed and thermally developing flow fields. So this is named after Graetz. It is reciprocal of Graetz number x by d REPR, where Graetz number is given by d REPR divided by x. Fully developed values are independent of Prandtl number. Fully developed conditions are reached for x by d divided by REPR close to 0.05. That we can see from here. That, at 0.05, this fully developed condition is reached. Of course, 0.05 is x by d divided by REPR. For constant surface temperature condition, it is desirable to know the average convection coefficient in the entry length. For use with the equation, if we try to use Q convective equal to average convective heat transfer coefficient, heat exchange area, that means area, wall area, into log mean temperature difference. We mentioned about it a few lectures earlier. Hansen presented the following correlation for hydrodynamically fully developed flow, of course laminar flow in tubes at constant wall temperature, which is given by this. Okay, so basically this is at the entrance for hydrodynamically fully developed but thermally fully developing, and basically this is average Nusselt number based on tube diameter. Because the above result is for thermally developing flow, it is not generally applicable. For simultaneously developing flow, a suitable correlation due to Cedar and Tate is of the form Nusselt number based on diameter, average Nusselt number is given by 1.86 Reynolds number into Prandtl number divided by L by D to the power 1/3 into mu by mu W. This mu W means value of the viscosity at the wall temperature to the power 0.14. All properties are evaluated at Tm, that is the mean temperature, mean outlet temperature from the tube and mean inlet temperature to the tube. So this is mean outlet temperature from when the fluid is heated fluid comes out, and it is a mean temperature of the fluid when it is at the entry divided by 2. These are bulk mean temperatures. So all the properties are evaluated at Tm. The viscosity of the fluid, mu W, this is at the wall temperature. Now convection correlations for non-circular tubes. This is also important. I would like to mention it here. To a first approximation, many of the circular tube results may be applied by using hydraulic diameter as characteristics length, which is given by dH equal to 4 AC by P. AC is the flow cross-sectional area and P is the weighted perimeter. However, in a non-circular tube, the convection coefficients vary around the periphery, approaching 0 in the corners. For turbulent flows, that is for Reynolds number greater than 2300, often it is reasonable to use the modified, that means instead of D, DH circular tube correlations. However, for laminar flow, the use of circular tube correlations is less accurate. For such cases, Nusselt numbers corresponding to fully developed conditions may be obtained from Shaw and London's book that I have mentioned, and I have already mentioned about compilation of Shaw and London's results, for the case of pipe flow or for the case of flow through tubes. And this is a table given basically for constant wall heat flux or uniform wall heat flux, constant wall temperature or uniform wall temperature, fully developed condition, the value of Nusselt number. So for circular tube, we have already seen for hydrodynamically fully developed and thermally fully developed flow. For constant wall heat flux, it is 4.36. For hydrodynamically fully developed and thermally fully developed flow for constant wall temperature, it is 3.66. We can call it constant wall temperature. We can also call it uniform wall temperature. Similarly, we can use the phrase constant wall heat flux or uniform wall heat flux. So these are the values. Now with different cross-sectional ducts, we have tabulated the values, and finally for parallel plate channel, when you can see basically this is B is infinitely large, so B by A ratio is infinity. There for constant wall heat flux, it is 8.23 fully developed, thermally fully developed and hydrodynamically fully developed flow. Similarly, hydrodynamically fully developed and thermally fully developed flow for uniform wall temperature, it is 7.54. And for uniform wall heat flux, it is 8.23. For tube, for uniform wall heat flux, it is 4.36. For uniform wall temperature, it is 3.66. So this table is useful for values of Nusselt number when we want to apply it for the ducts with different cross sections. Thank you very much for your interest. Thank you.